Okay, forces on inclines. The trick here is that we're going to use the mg of the object, in this case 180, so I'm going to draw a free body diagram. 180 newtons is the amount of gravitational force acting on it. Now what's going to happen is, to find the component of the gravitational force that acts normal to the surface, I'm going to use the cosine function, and to find that part of the gravitational force that acts parallel to the ramp surface, I'll use the sine function of this angle. So what I did is I went ahead and said 180 times the cosine of 30, and that gave me this value right here, 156 newtons. Now that's what's going to be acting normal to this. And then I did the same thing. I did the same thing again. I said 180 newtons times the sine of 30, and that gave me 90 newtons. Now that 90 newtons is actually acting in this direction here. So I have two forces. I'm basically resolving this 180 into two forces. The normal forces, which is 156 newtons, and 90, which is pulling down. But if you notice, there's a block stopping it, which makes a new normal force. So this is kind of tricky. So I've got 90 newtons of gravitational force working this way, and this surface here is placing a normal force in the opposite direction with 90. So this is what my free body diagram should look like. And by the way, well, as long as we're talking free body diagrams, a free body diagram should just be that. It should be a body that is free of everything else. I shouldn't see the ramp, I shouldn't see the stop, I shouldn't see anything other than the object and the forces acting on it. Now, so let's look at number 2. So in this case, a diagram shows a 15 kilogram box on one of those lovely frictionless inclines that acts at 30 degrees. A rope is pulling it up with a 45 Newton force. So the first thing we're asked to do is to draw a free body diagram showing the directions and numeric values. So I always start with mg. So here's 15 kilograms is going to produce 150 newtons of mg. So remember, g is 10. At least we're going to use it as 10. So that's 150. Now I'm going to say 150 times the cosine of the angle, which is 30, gives me 130 newtons, and that is acting normal to the surface. And in this case, I don't have to calculate what the component, which is this weight. I'm going to do it because I got a feeling I'm probably going to need it. So I'm going to go ahead and say 150 newtons times the sine of 30 is going to give me 75 newtons. But I don't put that on my free body diagram because technically that's not an actual force acting on it. It's just a component of this force. The normal force is actually pushing up on it. Okay, so let's see. So there's my free body diagram. I've got the 45 newtons of tension force. I have the 150 newtons of gravitation. And I have the normal force of 130, with which the surface is pushing up. But I'm going to need the 75 later, I got a feeling. It's always a good idea to calculate it. So what is the normal force acting on it? Well, it's 130 newtons right there, which I got by saying 150 cosine of 30. Now, C says, what is the magnitude of the component of gravitational force? And that's what I did here. So I basically said 150, which is the gravitational force, times the sine of the angle. And that gave me 75 newtons, which is acting this way. Now, how fast and which way is the box accelerating? To figure out acceleration, it's always the same. Acceleration equals the sum of the forces divided by the mass. A equals F over m, but it's got to be the sum of the forces, the net force. So let's find the sum of the forces. First thing we know is that this object is not going to be accelerating in this direction. The acceleration is going to take place in these problems always along the ramp surface, parallel to the ramp surface. So it is the forces acting parallel to the ramp surface that we're interested in. Now we know we have 45 newtons pulling up, and we have 75 newtons pulling down, so we'll call that negative. So if we find the sum of the forces, we're going to say negative 75 plus 45 gives me negative 30 newtons. So I have 30 newtons acting in this direction here. I'm just going to draw this in. I have 30 newtons acting this way is what the net force is. And that 30 newtons is acting on this 15 kilograms. So if I come over here and say the acceleration equals the sum of the forces over the mass, the sum of the forces is negative 30 newtons, the mass is 15 kilograms right here. So therefore it will accelerate at 2 meters per second squared down the ramp. Oh no, my surface isn't frictionless anymore. Arg. Okay, so the coefficient of kinetic friction acting on this 25 kilogram crate is 0.22. The box is currently moving up the ramp at 3 meters per second squared. Alright, so now first I'm going to draw a free body diagram. Alright, so I draw a body that is free of the surface. And I know that I always start off with mg, so 25 kilograms times g gives me 250 newtons in a downward direction. Now what I do then is I need to figure out what the normal force is before I can go forward. So what I had to do then is I had to say 250 times the cosine of the angle, which in this case is 40 degrees, and that's 40 degrees. And that's going to give me 192 newtons of normal force. So now that I have that normal force, I can use that to find the force of friction. So remember, the force of friction equals, well, let's just write it down. The force of friction equals mu, which is the coefficient of friction, times the normal force. Now, I just figured out the normal force is 192. So I would say the force of friction equals mu, which in this case is 0.22, times the normal force, which acts here, which we calculated to be negative 192. So when I multiply negative 192 times 0.22, I get a friction force of 42, which I will now put in my free body diagram because that is an actual force acting on it. And since the object is moving up the ramp, friction always acts in the opposite direction. So I'm going to draw 42 newtons in the downward direction. This would be the properly drawn free body diagram in this case. Now, what is the magnitude of the component of gravitational force acting parallel to the ramp? So this is the one I'm not allowed to put on the free body diagram, but let's just go ahead and figure out what this is. Basically, all I have to do is take the magnitude of the gravitational force, and to find the part acting parallel to the surface, I multiply by the sine of the angle. So the sine of 40 times 250 gives me a down ramp of force of 106 newtons, which is acting opposite to motion, so I'm going to label it negative. So what is the acceleration of the box as it moves up the ramp? Well, remember, acceleration always equals the sum of the forces divided by the mass. So we got to find the sum of the forces acting parallel to the ramp surface. So the sum of the forces in this case would be negative 106, which is the force of gravity acting this way, but we also have the force of friction acting in the same way. So these two forces are going to combine. So negative 106 plus negative 42 is going to give me negative 148 newtons. That's the amount of force that is going to act to cause this object to slow down as it moves up the ramp. So now I'm going to take Newton's second law, and to find the acceleration I'm going to take the sum of the forces, which is negative 198, and I'm going to divide it by the mass of the crate, which is 25, which gives me a negative acceleration of 5.9 meters per second squared. Now that I know the acceleration, I can do some kinematics. How far up the ramp will the box go before it comes to rest? Well, I know it started off at 3 meters per second squared, and I know it's going to end up at 0. I don't know the time, so this would be the best kinematics equation to use. So let's just look here. So I know that the final velocity of the box is 0. It comes to a rest. I know it started at 3, so that's my v0, and I'll square it. Plus 2 times the acceleration, which is negative 5.9, is going to give me delta x. So in this case, when I solve this, basically what I would do is I have to subtract 9, which is what this is, to get it over here. So I have negative 9 divided by 2 times negative 5.9 gives me 0.6 meters, 7.6 meters. So the object will slide up 0.76 meters, or 76 centimeters, and come to a stop, which seems like a reasonable value. Well, here's a classic, the skier on the hill. It's never a snowboarder, I notice, it's always a skier. Alright, so I have a skier in this diagram. The skier has a mass of 55 kilograms, and therefore I know that the downward force of gravity is going to be 550. So mg is 550. So I'm just going to go ahead and draw a free body diagram, and I'm going to put the 550. I always start off with that. Now let's see. What I'm asked to find is how fast she is going to be going when she passes the finish line, which is a kinematics problem. To solve a kinematics equation, I've got to know the acceleration. And the acceleration is not 10 because she's not falling down. She's going down the slope. So I have to take some things into account. I have to take into account the angle. I have to take into account the fact that this is a surface that has friction, and the coefficient is 0.6. And anytime you have objects moving on an incline where you have friction, you got some work ahead of you. Because the first thing you got to do is figure out the normal force. So the way I'm going to find the normal force is the force acting normal to this person is going to be equal to the cosine of the angle times this. So if I say 550 newtons times the cosine of 25 degrees, what I get is 498 newtons. So I'm going to put that 498 on my free body diagram. Now that I know I have 498, I can use that to find the coefficient, times the coefficient of friction to find the force of friction. So the force of friction always equals mu times the normal force. Now I found that the normal force is 498, so I'll put 498 here. I was told that mu is 0.06, so I'm going to put 0.06 here. 0.06 times 498 gives me a friction force of 30 newtons, which I then label in my free body diagram. Now I wasn't asked to do a free body diagram, but the truth is, guys, we draw free body diagrams to help us see the picture of what's going on here. Now, again, what I don't put on here is there is a gravitational component, which I better figure out. Now that gravitational component is going to be the force of gravity, which is 550 newtons, times the sine of 25. And that is going to give me 232 newtons, which I calculated right here. The force of gravity equals 550 times sine 25 gives me 323. So now I have this person sliding down. Let's think what I've got acting on this person. So this person has 232 newtons of force, gravitational force, pulling them down. There's supposed to be a 2 there. And this person also has 30 newtons acting in the opposite way. Alright, so what I have to do is find the sum of the forces. So I'm going to go ahead in this case. Yeah, it's a good idea to make motion the positive. Just say the direction of motion is positive, even if it's downhill. That's because it's really not down. It's not down. It's just in the downhill direction. So that's a fairly common convention to use. That whichever way you're moving is the positive direction. So I'm going to say 232 newtons minus 30 newtons of friction gives me 202 newtons as the sum of my forces. Now that I know the sum of my forces is 202, I can use Newton's second law. Acceleration equals the sum of the forces over mass. Man, we seem to use that a lot, don't we? So, 202 newtons, which is the sum of the forces acting parallel to the hill, divided by the mass of my skier, gives me an acceleration of 3.7 meters per second squared. Now, I know the person started off at 22, and I want to know how fast they are when they finish. So I'm going to use this kinematics equation. I'm solving for V final. So the initial V naught is 22 squared plus 2 times the acceleration, which is 3.7, times the delta x. Between here and here, the person is going to delta their position 100 meters. And when I run these numbers through and then take the square root to find V, I find it's 35 meters per second. And that seems reasonable. Think about it. She's going 22 here. 100 meters later, she's going 35. These are realistic values. This next one, all right, now you might have noticed I'm trying to put the more difficult ones towards the end of the assignments. So let's see what we've got here. I've got a truck. All right, I got a truck that's got a crate in it, and it's let's see, I have a 950 kilogram crate, and there's a coefficient of friction of 0.4. So the first thing I'm going to do, so well, A says in the space next to the diagram, draw a free body diagram. So here is my crate minus the ramp and the hill. It's a free body now. I'm going to draw mg. I always start with that. Now, in order to find this one here, the force normal, I think you know by now, I took 950 and I multiplied it by the cosine of 20, and that gave me 893. Now that I know what the force normal is, I'm going to go ahead and find the force of friction. The force of friction is the normal force times mu, and I was told the coefficient is 0.4, so that gives me 357, whoops, I forgot to write newtons after it, 357 newtons of friction force, which I then draw this way, because the box wants to slide this way, so therefore friction is acting that way, if you think about it. So the box wants to slide this way, friction is keeping it from doing it. Friction always acts against the motion of the object, or the way the object wants to move. The direction it would move if there weren't friction. So now, what is the magnitude of the gravitational component? Well, then I'm just going to take the 950 newtons and multiply it by the sine of the angle. So I get 325 newtons are pulling this way. I'm just going to go ahead and put that on here. I have 325 newtons acting in this way, and I have 357 newtons acting that way. Alright, so now, what is the lowest coefficient of friction I could have to keep it in static equilibrium? Well, that means that right now, the way I have it, there's more upward friction than there is downward pull, which keeps it from moving at all. Friction is never going to cause it to move uphill. Is if this force exceeds this force, it will begin to move. Now, think of it this way. All right, first of all, let's just see. So basically, the minimum amount of mu would be found by saying, you know what, if we had 325 in this direction as well as 325 this way, that'd be the minimum. So basically, I'm going to take this value here and say, all right, if I had a friction force of 325, what would mu have to be? Well, I know what the normal force is. It's 893. So I just solve for mu then, which means I'm going to say 325 divided by 893 gives me a mu value of 0.36. So what we have is 0.4, which is more than sufficient because it generates this much force in order to counteract this much gravitation. It would be possible to keep the crate here if the value of mu was only 0.36. Alright, well, let's see what we got now. Given that the coefficient of friction is actually 0.4, what is the fastest the truck could accelerate? Well, here's my approach to it. I would say, alright, let's just see, what is the difference between the amount of friction force and the amount of gravitational pull? So here's the force of friction that is pulling it up. Here's the amount of gravitation pulling it down. And what that leaves me with is I have 32 newtons of basically leftover force. So it's almost as though what I have is this invisible rope that will break if the force on it, if the tension force exceeds 32. So in a sense, really, 32 is the number I'm working with. 32 is the amount of force I cannot exceed. So I'm going to use Newton's second law, and I'm going to put 32 newtons here. I'm going to say 32 newtons, and I'm going to have acts on a mass of 95. The acceleration is 0.34. If I accelerate faster than 0.34, it's going to cause the amount of downward force to exceed that of the 357 newtons of friction force that holds it in place. Don't feel bad if that one was a little bit much. Now this next one it's ugly. Well, let's just start with A. All right. What is the magnitude of the component of gravitational force acting parallel to the ramp? Well, we've been here before. All I had to do is take mg, which is 200, and I'm going to multiply that by the sine of 30. So 200 times sine 30 gives me 100 newtons. That's how hard gravity is pulling this way. Gravity is pulling this way with 100 newtons, which I'm not allowed to put on a free body diagram. Now the second question is, if the surface is frictionless, what is the magnitude of this force that would be necessary to keep the block from sliding. That means it would have to produce 100 newtons of upward force to keep the box from sliding. Now, which component of this force would that be? Well, if I come in at this angle, this would be my cosine and this would be my sine. So what I'd have to do then is I'd say, alright, whatever this is, we'll call it x, x times the cosine of 30 is going to have to produce 100 newtons of force to keep this from moving. So x cosine 30, that means to solve it, x equals 100 newtons divided by the cosine of 30 equals 115 newtons. If this is a frictionless surface and I push this way, basically parallel to the floor, I have to push with 115 newtons of force to keep the box from sliding. Conversely, if I just push straight up, I don't have to push with 100. It's this last one that, oh my gosh, why did I ask you this one? Alright, well now I'm telling you, the coefficient of friction is 0.3. It's no longer frictionless. The magnitude of force A is now 400 newtons. And what I want to know is, how fast and which way is the crate going to accelerate? Well, the first thing I have to do is figure out what is the total normal force acting on the system. So I have one component of normal force, which is produced by the fact that this is a 200 kilogram box. So 200 times the cosine of 30 gives me 173 newtons of normal force caused by the weight of the box. And then I have 400 times the sine of 30 gives me 200 newtons of force caused by the box pushing. It's really frustrating because gravity is acting this way on this slope, so I have to use the cosine to find this. But this is acting at an angle to this surface, so I have to use the sine. That's tricky. I agree. So basically then the normal force, the sum of the normal force is going to be the 200, which is caused by this, creates 200 this way, and gravitation causes 173 this way, so the net force normal is 373. Now that I know what the total normal force is, I'm going to go ahead and take mu, which is here, so 0.3, which is mu, the coefficient of friction, times the normal force, gives me a friction force of 112 newtons. So there's 112 newtons of force that's trying to keep this box from moving. Now, let's figure out what the sum of the forces acting parallel to the ramp are. So the forces I have are the component of this 400 that's acting in this direction. So 400 times the cosine of 30 gives me 346 newtons pushing up. So I have 346 newtons of upward force trying to cause it to accelerate upwards. Now, I've got 100 newtons worth of gravitational force that's pulling it downwards. And I have 112 newtons worth of frictional force that's also working in downward direction, taking away from this. So 346 minus 100 minus 112 gives me 134 newtons of upward force on this object. And now finally I can find acceleration using Newton's second law. The sum of the forces divided by the mass, 134 newtons, which is my total force parallel to the surface, acting on a 20 kilogram box will cause it to accelerate at 6.7 meters per second squared up the ramp. I don't blame you if you said, screw this last part.